Hello, good morning, everyone. I hope you are hearing me well. Let's start today's joint webinar. I welcome you all for the joint webinar between three projects on the topic of building the future of second life energy storage in Europe. These three projects are from the Horizon Europe funding scheme in the year of 2023, so they are running for around 2 years. And today they will present their latest progresses with our speakers. Moving forward, it's good to know for you that the slides and the recordings will be shared with you, so no issues. And feel free to write your questions in the chat and comments as well during the presentations. After each presentation, we will have 5 minutes of question and answers, and we will try to cover as many questions as possible. We have three speakers today from representing three different projects. I will be your moderator of today's webinar. My name is Sajjad Hussain, working as a research professor at the Free University of Brussels. We have today as a first speaker, George Constantinidis, who is working as a research and project manager in the Institute of Communication and Computer Systems, named as ICCS in Greece. He will be representing the Battery to Life project. Our second speaker today is Yosu Olmos, who is also a research and project manager from ICALAN, a Spanish research institution representing the Big LEAP project. And our third and the last speaker would be Andy Rose, who is representing the REBORN project, and he's working as a mechanical engineer specialist in battery systems in the Research Institute of CEA in France. So without spending more time, let's look at the agenda of today. Our speakers will talk on two different types of topics. And the first, we will start with the cloud BMS and the battery digital passport from George. Then we will have SOX and RUL algorithms development from the project of Big Leap by Yosu Olmos. And then we will, Andy Rooks will talk about the soldierless modules from the Reborn project. After the presentations and the Q&A, we will have a round table, rather round screen, on the topic of current challenges on the second life, where we will also address your questions. Good. Now, probably we can move on to our first speaker, who is George. George, please feel free to go ahead.
Hi. Thank you for the introduction. Let me share my screen. Okay. Can you see my screen? Can you see the presentation? Right?
Yes. All good.
Okay. That's perfect. Thank you for the introduction, Sajjad. Good morning, everyone. Today, I will briefly present how the Battery to Life project approaches cloud battery management system architectures and how this supports the digital battery passport and the concept of state of warranty. The next minutes, I will first briefly introduce the project and explain why this topic is particularly relevant today. Then I will present the cloud BMS architecture developed in the project, and finally I will discuss how advanced analytics enable state of warranty estimations through battery prognosis algorithms. Let me start with a short overview of the Battery to Life project. Battery to Life is a Horizon Europe project focused on battery management systems and system design for stationary energy storage using second life batteries. The project runs for 36 months from January 2024 to December 2026 and includes 11 partners from 5 countries. The project is coordinated by Dr. Angelos Amnitis from the Institute of Communication and Computer Systems. The Battery to Life project investigates two complementary use cases for stationary energy storage. The first use case focuses on domestic energy storage system in Austria, where the system's design incorporates second life consideration already during the first life design phase. In this case, the battery system architecture is developed so that it can be more easily repurposed and reused in stationary applications at the end of the first life. The second use case focuses on industrial or grid-scale storage in Greece, where batteries that have completed the first life in electric vehicles are repurposed for second life applications. The overall goal is to enable safe, reliable, and economically viable second life battery systems through advanced BMS, battery management systems technologies, and digital tools. Finally, the project funding is approximately 4 million euros. This topic is particularly important today for three main reasons. First, regulation is changing the rules. The new EU battery regulation introduced the concept, as you may know, of the digital product passport, which also the digital battery passport is a part of it, and requires life cycle traceability, performance transparency, and responsibility, which is extended in the second life of battery. So it makes us to have a better product as it will be used after the first life. Second, we are seeing massive growth in the second life battery market. Large numbers of EV batteries will soon reach the end of their first life and can be repurposed for stationary storage. In this way, second life batteries can address two important challenges: reducing the number of batteries that need to be recycled premature. As you know, the battery of EV need to be replaced at 70 to 80% of state of charge, and supporting the growing demand for stationary energy storage. Third, the energy sector increasingly requires bankable and durable storage assets. However, second life batteries often come with uncertainties such as unknown degradation history and unclear warranty liability that we are trying to solve also in the battery to life. Advanced analytics and data-driven battery management can help address these challenges. So, the EU battery regulation introduced the digital battery passport, as we mentioned above, which will provide structural information about batteries throughout their life cycle. The passport includes several categories of data, such as battery identifiers, technical characteristics, performance and durability parameters, state of health indicators, sustainability metrics, and lifecycle usage data. All this we're trying to incorporate in the cloud platform and in our developments in the project. This means battery will increasingly be managed as data-driven assets where reliable operational information is essential. However, second life batteries introduce a significant trust challenge. As we know, it is have been already used, so we have to build this trust. These batteries inherit heterogeneous aging histories and operate under new application conditions, which creates uncertainty regarding performance and reliability. Some key challenges include limited transparency about first life usage. Sometimes we don't share this data with other as many brands. Changes in operating conditions during second life, static warranty frameworks designed for first life application only, and the lack of continuous lifecycle intelligence. To address these issues, we need continuous condition monitoring and advanced lifecycle analytics, which where cloud-enabled PMS architectures become very important and essential for this effort. Traditional battery management systems operate mainly at the device level, focuses on real-time monitoring and safety control. However, the usually have limited computational capabilities and limited ability to perform long-term analysis. In battery to life, we extend this concept through a hybrid edge cloud architecture, where the edge BMS performs real-time functions such as state estimation and protection, which is very essential to do it in very limited time. And the cloud platform performs advanced analytics, including diagnostics, degradation modeling, and predictive algorithms. This combination allows much deeper analysis of battery behavior. The cloud BMS does not uh, complement the edge BMS. It can be replaced, as we need also to monitor the edge BMS. So the cloud BMS platform is built around several function layers. At a high level, the system connects the embedded BMS at the battery level with external services and stakeholders through a cloud platform. Data flows continuously from the edge BMS to the cloud, and the insights can also be shared with external applications and stakeholders. And the architecture includes 6 main modules that I will explain in the next slides, which is data ingestion, API gateway, security module, analytics engine, database and storage, and the monitoring dashboard. All these components form the digital backbone for battery lifecycle analytics. I will start with the data ingestion layer that collects operation data from the edge BMS unit. This enables continuous tracking of battery state and operation parameters. The system also supports remote firmware updates, which allows improvement and updates to be deployed remotely. For example, in Pillar 1, electrochemical impedance spectroscopy measurements are used to improve battery diagnostic, and these EIS parameters can be updated and improved through a third-party services connected to the cloud platform. So the next one is the API gateway, provides standardized interfaces so that third-party application can interact with the platform. And security is also a key aspect of the architecture. The platform includes authentication systems, role-based access control to ensure that data and services remain protected. The data processing and analytics engine is where the main analytics algorithms are executed.
George, do you hear us? Do you hear us, George?
Yes.
Yeah, so I think the screen was a bit frozen.
Okay.
So
Can you
we
hear me
lost.
now?
Yes, we can hear you clearly. We just lost, let's say, last 10-15 seconds.
Ωραία. Okay. Regarding the monitoring and data and management dashboard, should I begin from there?
That's fine. You
Ωραία.
can start from this slide.
Okay. Okay. Perfect. Perfect. Thank you. So sorry for the inconvenience. I don't know. Things happening in online meetings. As I was saying, the data processing and analytics engine is where the main analytics algorithms are executed. This includes diagnostic algorithms and predictive analytics models that we can see later on. All operation data is stored in a database and storage layer, which keeps both raw and processed data from the edge system and other data sources, as for example, for third-party services. Finally, the monitoring and management dashboard provide visualization of battery parameters, operational analytics, and system health to the stakeholders. This allows different stakeholders to access relevant information through user-friendly interfaces and based on the role that they have been provided by the system. Within the digital battery passport, it's important to distinguish between static and dynamic data. Static data is defined at the manufactured stage and remains constant throughout the life cycle. So the first life and the second life, it is been forward. Example includes battery identifiers, manufacturer information, chemistry, and design parameters. And the dynamic data involves during operation. Examples include state of charge, state of health, remaining useful life, and operational history. All this data can be accessed based on the role of each stakeholder. For example, the public can also scan the QR code of the battery and have access to some of this data, but all this data depends on the role that each stakeholder have been granted. Um, Okay, so now I will introduce the state of warranty that have been developed in the frame of the battery to life. State of warranty is a key concept and dynamic indicator that describes the remaining warranty validity battery based on its condition and predicted degradation. Unlike traditional warranty models, which are static and based on predefined limits, state of warranty use operational data and predictive models. This enables more accurate monitoring, very important in the second life batteries.
Georgie, we cannot hear you anymore.
I will change the Wi-Fi. Sorry.
Yeah, you are back.
Sorry, I will change the Wi-Fi connection. I don't know what happened. I will put my mobile hotspot. Just give me one moment. Sorry for this.
No problem.
Can you hear me now?
Yes.
Yes. I changed to my mobile hotspot, so thankful it will be work. Uh, Sorry again. So uh, let's begin with the how the algorithms have been developed. It combines three main elements: prior knowledge, real-life state of health updates, and the stochastic filtering approach. First, the prior knowledge is obtained from the expected use of the battery together with an aging model. These have been provided by the battery manufacturer of the project. In this project, the aging model is a power type equation which was built using aging data provided by the manufacturers. The parameters of this aging model are treated as hidden states within the stochastic filtering framework. These parameters are continuously updated based on the state of health estimations obtained during operation. In this way, the model evolves as new data becomes available, allowing it to better represent the real behavior of the battery. It's very important. The stochastic filtering method used in this work is a particle filter. The particle filter learns the real aging trend of the battery from the observed state of health data. It helps remove measurements noise and accounts for uncertainties in the state of health estimation. Before applying the particle filter, its high parameters must be optimized. This is done using Bayesian optimization, which is a machine learning method used to find the best configuration for the filter parameters. It's shown the particle filter results and theoretical second life scenarios. I think if you can see there is small deviations, but it's close to the real life. It can be also been explained. If the person from CIDIC is here, if you have any questions. Finally, the output of the prognostic analysis is the estimation of the remaining useful life. The remaining useful life estimation is essential for determining the state of warranty. By predicting how long the battery can continue operating before reaching its end of life threshold, the system can provide early alerts that you can see in the image below and support predictive maintenance strategies. This allows state of warranty to identify potential issues before significant degradation occurs, improving reliability and reducing risk in second life battery application. This makes it more appeal to the public to accept that kind of batteries. Even the upside down, so I think I'm on time. Thank you very much for your attentions. We'll now proceed to the QA session. Also, if any question arises later on, please feel free to contact me directly. Depending on the topic, I can connect you with the relevant battery to life partner.
Okay, thank you, George. Still, you are right on time with the hiccups, but no issues. This is a modern day problem. Okay, so I also invite all the audience to ask your questions and use the chat to ask your questions. In the meantime, we receive some questions. Maybe I have something to ask. So this state of warranty is a very interesting the state that you explained you are developing in the battery to life. I was wondering that what is the impact of the first life use, because we are using the repurposed batteries. They are used in a vehicle in the first life. What would be the impact of the first life use in your state of warranty calculation?
I don't know if it is someone from CIDIC or I will try to answer this question. But the impact it is been all the data from the first life. It's been assessed by the algorithms, and then it can provide a new. We're here. Sorry, Valdera, can we give access to Mikel Arianda in the microphone so it make a more appropriate response to the question?
Yeah, you should have access to the Microsoft, to the microphone.
Okay. Mikel, can you
Hello,
open
Mikel.
your microphone?
Just give me a second.
Okay.
Can you hear me?
Yes.
Yes, Mikel.
Okay, perfect. So nice question regarding which is the impact of the first life in a second life application and how it affects the state of warranty. So the good point of the state of warranty is that you define before starting working with the second life which will be the warranty for this second life. And the aim of this state of warranty estimator is to track what you define at the beginning. So in reality is a tool to be able to as a track which is the deviation or the changes in this definition of warranty. So in the first life is the same. You define a first life warranty, maybe a time period, 10 years or 15 or whatever. And what you do is observe how it evolves. And thanks to the remaining useful life prognosis activity and other activities, you are able to, in a really simple color-based code, you are able to observe if everything goes well as expected, or if there is any early alert where you have room for action, or it is just too late and an action in batteries replacement is imminent. This is the idea.
Okay, good. Thank you for answering. Then maybe a general question that comes out to the second life repurposing battery projects all the time. That what have you defined as an end time of the second life? What is the SOH range that you are following in your project? Either George or Mikhail.
Yeah, Giorgio.
Can you continue or?
Yeah, I mean, this is really battery dependent. So in this case, I would say that we are working with two use cases, and the owners of the battery are the ones that define up to which stable health they want to use the batteries. So for us, it is I would say an imposed value based on the use cases.
Okay, thank you. Then we have one question we can still take is that someone was curious that what is the best RUL estimation model methodology, more hybrid models or models, AI-driven models like LSTM or artificial neural networks?
Yeah, nice question as well. This is there are many works in the literature dealing with how to estimate how to predict the remaining useful life. In our case, we adopt we are aspect also in modeling, so we have an expectation of how the agent will perform. So based on that, what we do is filter, I would say, the noise from the uncertainties. And for that, we use an stochastic filter called a particle filter. And then what we do is filter the noise of the uncertainties of the SOA state of health estimation, the uncertainties on the expected battery use, and all this. What we do is track the trend underneath this data, and we propagate this trend to determine which is the remaining useful life.
Okay. Thank you. Thank you both, George and Mikhail. We will address maybe more questions in the round table discussion. For now, I thank you for your presentation.
Thank you, Mikhail.
Now we move on to our second speaker, who is Yosu Olmos, will present their work on SOX and RUL algorithms and cloud layer BMS development from the project of Big Leap. So Yosu, you can share your screen and go ahead.
Okay. Thank you very much, Shazad. You can see properly my screen?
Yes.
I guess. Yes. Okay. Perfect. Thank you, Shazad, for this kind introduction. Also, thank you for all the organization of this webinar and for the invitation for this talk. So, as it was said, my name is Yosu Olmos. I come from Microland. And today, the topic of my presentation will be the state of X and remaining useful life algorithms and cloud layer BMS development. So as you see, it will be similar topics as the previous presentation. Also, in this case, I will present the developments that we have made in Big Leap project for these topics. Okay. So regarding the agenda, it will be quite simple. So I will make a brief introduction to the Big Leap project and also to the three main topics that I will cover today. These topics will be, as previously stated in the title, battery state algorithms, battery remaining useful life algorithms, and I will also make a brief description of the developments that we have made in the cloud system of Big Leap. And in order to close all the presentation, I will just list some important conclusions. So starting with Big Leap project. Big Leap is a project that comes from the same call as Battery to Life project. So we cover similar topics. So in this case, we are focusing on enhancing the operation reliability of second life batteries also, especially by addressing the concept of interoperability in battery management systems. Okay. So for this purpose, we are developing a 3-layer BMS architecture that I will present afterwards. And we are also focusing on developing and integrating an adaptable energy storage system design in order also to optimize the reconfiguration process of second life batteries. So the consortium of the project is composed of 16 partners. And I will just make a brief introduction to our institute, to Ikerland. We are a technology research center for more than 50 years, and we are especially committed to provide solutions to companies. So we try to bridge the gap between academia and industrial needs. And we are mainly focused on three main areas. Okay, digital technologies, artificial intelligence, energy mechatronics, and embedded systems and cybersecurity. But in my case, I came from the energy department. But as you will see, the topics, for instance, that we cover in this project, we try to give a holistic solutions to all the developments that are recurrent. Okay, so in this case, we make a fusion of digital technologies, energy, and also embedded systems in this project, for instance. Okay, and going into the topic of today's presentation. Okay, so we have state of X algorithms, we have remaining useful life algorithms. Both are important for operation of batteries. In the case of the state estimators, they ensure a safe operation. They are able to, or we can use their information to improve the performance or even to optimize the operation of the battery. Similar with remaining useful life algorithms. Okay, we consider these algorithms as the ones that are able to predict the future degradation trend of a battery. This is important because different operation patterns led to different degradation speeds. So we consider that there is a possible coupling between the remaining useful life algorithms with operation planners, such as energy management strategies, in order to optimize the future operation of a battery to avoid early degradation of these batteries. So these concepts, of course, can also be implemented for not only for first life, but also for second life. Okay, so in this context, in Big Leap project, what we aim is to increase the adaptiveness of these SOX algorithms in order to ease also their coupling between the first and the second life. Okay, because one of the main problems of these algorithms is that you need to especially adapt them for each battery chemistry or for each battery cell. Okay, so in this context, in order to increase this adaptiveness and in order to ease this, let's say, transition from first to second life, one of the explored techniques has been the application of transfer learning. And it's specifically what I will present today. And I will present it, or I will explain you what we have done and the application of transfer learning for both state of charge algorithms and remaining useful life algorithms. And then I will explain how these algorithms were integrated in a cloud environment. Okay, and of course in Big Leap we have made further developments, but today I will just focus on these two due to time constraints also. But if you have any question, you can contact me or contact any people from our consortium. So regarding the state estimators, from a general perspective, so we have developed an algorithm that gives the state of charge and the state of energy together, and we have selected one machine learning based method to develop these algorithms. You can here see the typical or the traditional flowchart for the development of machine learning based state algorithms. So normally we start from laboratory data, and let's say from laboratory data prior to the deployment of the application. Here we can obtain one, or we can train one machine learning model, but then this can be fine-tuned, or we can perform further trainings once that we have application data. Both are fused, and we are able to obtain a better or improved machine learning model. But in both cases, we are making a training from scratch, let's say. So here, what we propose is the integration of the concept of transfer learning. So because what we are able to do is to transfer the knowledge of previously trained algorithms to other type of batteries with fewer data requirement, let's say. So this third data set that is fused with the knowledge from previous models is able to train a third model that, for instance, can be focused on second life algorithms. And the important point here is also that the dataset 3 is much smaller than the previous dataset. So with this approach, we can efficiently reduce the required both development time and the required data needs for second life algorithms, and also for further battery chemistries or battery products. So applying this transfer learning technique, we have obtained some results in Big Leap project. So we have first designed a baseline algorithm that provides at the same time the state of charge and the state of energy. As I have mentioned before, we are using as inputs of these algorithms the typical metrics that are available in the BMS: voltage, current, temperature, and also SOH. And we selected gated recurrent units based neural networks in order to train this model. And after training a baseline model, then we also tested different transfer learning techniques from NMC to NCA to NMC to LFP. And with the obtained results, we were able to demonstrate that we can reduce the training time and also the required amount of data, but maintaining similar results. Okay, so here you can see the comparison between training a model from scratch only with NCA data and applying this transfer learning in order to get the knowledge from MNC to NCA with a reduced database. And you can see that in both cases, for SOC and SOA, we were able to obtain similar absolute errors, what demonstrates our previous hypothesis. Okay, then we also perform a similar approach, but for the remaining useful life algorithm. Okay, so here maybe the most important point was to design a proper algorithm with the proper inputs, especially because as maybe a state of charge is affected by less variables than the degradation. Degradation is much complex. It includes many electrochemical internal processes. And in order to properly capture all of them, we define a long set of inputs, okay? And for that, we define some guidelines, okay? Because normally the set of inputs that you define for this algorithm, it will then affect the way or the ability of retraining, of applying transfer learning applications, or even the ability to couple these algorithms with energy management strategies. So we set some general guidelines, such as like the model can only be trained with features extracted from data monitored in real applications. The model has to map the relationships between operational conditions and the consequences. And we defined also that these relationships should be agnostic to calendar and cycling degradation. Okay, so from this analysis and these guidelines, we defined all this long set of inputs for the model, and we select feed-forward neural network as the machine learning model, and then we applied a similar exercise as with the state of charge algorithm. So first we developed a model from scratch with an NMC database, and this was just to demonstrate the design of the remaining useful life algorithm. And as you can see in the results obtained for the cells that were not observed during the training, the results were quite good, and we were able to capture even the trends, the degradation trends that were not used during the training of the model, and we obtained an error below 1% for these non-observed cells. And then we implemented also this transfer learning approach. We selected another data set. In this case, it was an LFP battery, and we applied the same exercise. We first trained the model from scratch, and then reduce the database and apply the transfer learning coming from the previous model. And as you can see, even in this case, we were a little bit farther away from the average error from the model of scratch, but we were able to reduce the training time from several hours to less than 1 minute. Okay. And then after the developments of all the algorithms, we also developed the cloud system for Big Leap project. So as you can see, we developed a 3-layer or even 4-layer if you also consider the BMS slaves. Okay, we have the slaves, the BMS master, the edge, and the cloud, as similarly as Georgios presented before for Battery to Life project. And we decided to divide the integration of the algorithms between both layers, between the edge and the cloud. In the case of the state of charge, the estimations are made in the edge, but trainings in the cloud. And in the case of the remaining useful life, we make both the trainings and estimations in the cloud. So I see that I am running out of time. No, Cesar? Okay, so I will go to the conclusions, and of course, if anyone has any question about the integration of these algorithms, just contact me. So as I have presented, Big Leap aims to increase the adaptiveness of SOX and rule algorithms in order to improve their coupling between first to second life. And one of the techniques that we explored for this was the application of transfer learning. So we have developed these algorithms with transfer learning. I have presented these results where we demonstrate that we can efficiently implement this transfer learning to speed up the development time of second life batteries. And we have also developed this 3-layer BMS that is able to increase the capabilities of the traditional embedded control systems, and especially the development of this cloud allows the implementation of these computational costly algorithms. So thank you very much. I will be happy to answer any question now, but as in previous cases, if you have any question, you can contact me. You have in the slides my email, and if I am not able to answer, I will forward the question to any important partner involved in Big Leap.
Okay, thank you, Yusuf. We have some time still to receive some questions. As a general reminder to all the audience today, feel free to ask your question. We already had one in the last presentation, which we could not address, but we can do now with you. So you have shown the number of parameters which are important for your RUL estimation. And the question is that which are the important RUL parameters?
Okay, so in this case, as I have explained before, we made let's say an analysis in order to try to capture all the important features in this model. So originally we defined that we need to, let's say, to model the effects produced by high and low temperatures, high and low currents, also high and low voltages. Let's say this is related also to the depth of discharge of the battery. Of course, also the effect of the course of time, the effect of how many cycles you have made to the battery. And essentially, those are all that are captured as inputs for our model. Now, we have the number of cycles, the time since the battery was deployed, the effect of different ranges of temperature, the effect of different ranges for the current, the effect of different, let's say, SOC ranges also. Yes, so essentially those are the ones that we capture. Of course, there are further that can be captured also, like the effect of pressure, but as we defined in the guidelines, we wanted only to train a model with features that can be extracted for typical industrial applications where, for instance, nowadays pressure is not measured yet, but in the near future, if this is also implemented in typical BMS systems, it should be another variable that should be also tracked in this kind of models.
Okay. The variables that you were presenting might create some confusion because in the bracket it's mentioned percentage of time. So are these variables are all time variables or?
Yes, because yes, this I can give more detail in this because the point here is that we use as an input the percentage of time that the battery has been staying in different temperature, current, and SOC ranges. Let's say if for instance, the temperature has been all the time at, let's say, 50 degrees, then this input will be 1, and the other ones will be 0. But if the battery is cycling between 10 and 30, then this input could be 0.5, the other one 0.5, and the others 0. So in this way, we try to capture for each time step of the whole lifetime of the battery in the past, how much time it has been working in a specific temperature, current, and state of charge ranges.
It's the same for the voltage ranges for the SOC.
The same for, yes, the same for the SOC, yes.
Okay. Then maybe a follow-up question is that for your SOC and SOE estimation, did you consider the SOH status?
Yes. So we considered the SOH status. So there are two options here. We can train the model with the SOH and without the SOH. We have trained both. We have tried with both options, but we have not made the analysis to compare the results for the whole lifetime, because of course the effect of the capacity of the battery is also translated to the voltage. Let's say with a lower capacity, the voltage evolves faster. So only with the only training your model with the voltage, somehow you will be able also to track this this effect of the SOH. But in this specific option of the algorithm developed in Big Leap, we have selected the SOH as one of the inputs of the model.
Okay, good. Thank you. I think we probably will discuss more on this topic during the roundtable discussion. Thanks again for your presentation, Yosu.
Thank you very much.
Now we will move to our third and the last speaker, Andy Rose from CEA, representing REBORN project. Andy, please go ahead and share your screen.
Okay, hello everybody. Can you see my screen?
Yes, all good.
Okay, perfect. So my topic is the solderless connection and what we've done on the REBORN project. So maybe at the beginning, it's good to have an overview of what is the REBORN project and what is the final goal of the project. So the REBORN project aims to equip the European battery ecosystem with a modular battery pack, including the BMS and the system design suitable for both first life and second life application. And the ultimate goal is to implement a stationary energy storage system capable of absorbing electrical energy generating from photovoltaic sources. So at the end of the project, there will be two demos. The demo one with this kind of cells. This is a prismatic cells, and especially they will be age. And these cells will be implemented into a module, and this module are gonna go inside a rack, and after this inside a big closet. And the demo 2 with mix age and new cells, push cells, that gonna be implemented to a module and also go to the closet. So this is the final global goal of the REBORN project. And from our side, we worked on the work package 5 called battery module pack and test bench design. And at the CA, we worked to develop the specific electrical solderless connection for the power tabs of the cells. So we worked on two types of cells, the push cells, it's NMC cells, and also on prismatic cells, this was LFP cells. Okay, so I'm gonna start to present what we've done on the low voltage module with the prismatic cells. What we can see on these cells is that they have one side in copper and one side in aluminum, and inside it we have a threaded hole, and we used this specificity to implement the solution. So our reference solution was just a MC screw with Belleville washer. This is our reference solution. We also tried the cam lever solution. This is our number 2 solution. We have the rivet pin solution. So this solution have an expanded socket and a pin, and when we push the pin, it extends the socket. So it's kind of the same as what you have, the same as the moly solution you put on the wall, but this one permit to withdraw the pin when to permit the demontability of the cells. And we have this group of 3 solutions. I will call them a pin and socket solution because you have a pin and a socket, and the contact is made by lamella inside the socket and around the pin. And this is what we're gonna test electrically. So we have 2 kind of Molex pin and socket. The difference is that on the floating socket we have 1 millimeter adjustment, so it's permit to have slightly move of the pin or the bus bar, depending on what move. And the other one is a Ratasock solution. So this is kind of the same. You have a pin and a socket, but the contact is made differently inside the socket, and this is what we want to compare. So for each connection, we used our test bench. So we have 2 power cable that are connected to manufacture fake tabs. And on these fake tabs, we put our solution, and the contact is made by our bus bar with the solution integrated in it. And we have temperature measurement and also voltage drop measurement that we placed on the connection to see the voltage drop around the connection. So for each solution, we had some question, and before testing electrically this connection, and every graph below are answering some question we had. So the first one was at what tightening torque does the voltage drop stabilize? Because we have screw solution, we need to know at which torque we have to apply on the pin to have a good electrically connection. So here we have the average voltage drop in function of the torque, and what we can see is that at some point it decreased and at some point it stabilized around 4 or 5 Newton per meter. And we have also the value of the voltage drop that we can compare to other solution. You will see next slide, not next slide, but after the presentation of all the solution. We also had another question. Does the increase of the current affect the voltage drop? And what we can see here is that we have a straight line, a linear line. So that means that the resistivity is constant. So that was good, because what we don't want to see is that at some point when the temperature rise is too much, at some point the resistivity increase, and that means that there is degradation around the connection. And another question was, what is the proportion of voltage drop between the pin and the socket? Because here we have two contacts, one from the tabs to the pin and one to the pin and the socket. So basically what we can see is that we have approximately 50-50% of the contribution are from the tabs to the pin and 50 from the pin to the socket. So this kind of information is interesting to know more about the connection. So we've done that for the Amphenol solution also. So we have this graph at some point is stabilized. We also have a straight line, so it's not degraded in function of the current, and we are good with this connection. We have the voltage drop, so we can compare all the solution, and it also 50-50 in terms of proportion of voltage drop on the connection. We also done that for the cam lever, where the voltage drop is really low. And what is interesting with this solution is that if we have, imagine a fork bus bar, so you have something here, you can release, when you release the cam lever, you can just pull out the bus bar and you can change the cells or anything else. And what we can see is that because we have a really low voltage drop, even at 100 ampere, during 1 minute, the temperature rises just 0.2 degrees, so the connection was really good. Since the beginning, I just show you what was good, and the connection were good. But for this one, that wasn't the same. So on this test, I've done 5 repetition on each connection. So I repeat the connection 5 times, because I wanted to see if the connection was reliable. Because on the 2 first tests, I was around 20 millivolt drop. So that was our threshold inside the specification. But I wasn't sure about the repeatability of the solution. So I made 5 tests, and what we can see is that we have a lot of dispersion around the value that we get. So the conclusion was the solution wasn't good for the application, and it's not really reliable and repeatable. And also, if I'm looking just around the best one, the repetition number 2, and I increase the current, at some point there is a break on the curve. This means that there is degradation on the connection. So this is what we don't want to see. And finally, this is the graph. We can compare all the solution with our threshold of 20 millivolt. And what we can see is that all the solutions are below the threshold, not the rivet one, because the reason I explained the previous slide. But we have all the value of the voltage drop for each connection at different ampere. And this is interesting to make the choice of which connection we're gonna use inside the module. Another question we had, because we're gonna use the age cells, is what is the impact of age tabs on the voltage drop? Because on the test bench we used, it was fake types with new copper and aluminum tabs. So we have done the exact same as the test bench, but now with real cells on a climate chamber to have the value of the voltage drop with second life tabs. And what we can see is that on the aluminum side, we have plus 20% of the voltage drop, and on the copper side, -7. I don't know really how to explain this value. Maybe it's the alloy we used on the test bench that wasn't really the exact same as the real tabs. But basically what we can say is that we are below the threshold of 20 millivolts. So that was good for our solution. So with our partner, we choose this solution with the floating socket Molex with 1 millimeter gap between inside the solution. So this is what we're gonna use inside the module. And now we have to implement this solution at the module level. So we have all the pins there on the terminal, and we have the socket inside a power PCB. So now to make the connection, we just have to put down the PCB on the pin and the connection is done. Okay, so now I can talk a little bit about the solderless connection on the push cells for the HV module. So it's not exactly the same. It's kind of harder to have a solderless connection on the push cells. But one solution we found is what I called the sandwich solderless connection, because you have a lower plate where you fold the tabs. You have a bus bar between the lower plate and the upper plate, and the upper plate compress the tabs on the bus bar on the tabs with the screw around. Maybe it's clearer here. So you have the lower plate, you fold the tabs on it. You have the bus bar you put between, and you have the upper plate and the screw around. You press the bus bar on the tabs. And the value we get on the test bench was 10 millivolt drop from the aluminum tabs and 15 millivolt drop on the nickel plated copper side. So basically it was 10 times below the threshold we fix with our partner. So that was a good result for our connection. In terms of temperature rise, we had 8 degrees over 30 minutes at 1C condition, so that was acceptable also. And this solution has been implemented inside the module and gonna be implemented to the pack level and be dismantled after this to go to the demo 2. And finally, yes, I have the time to talk about the other goal of the REBORN project. So I've talked about the solderless mechanical interconnection, but we will also do wireless RF communication between the cells and the BMS. There will be also during this project algorithm to the cell aging of cells. There will be also the implementation of a battery passport because we're gonna use the small life cells, and we have to know where they come from and what is the health status of the cells. And there will be also a post-characterization process for first life batteries. And also there will be a semi-automated robotic dismantling controlled by virtual reality to dismantle the pack I showed for the HV module. And at the end of the project, there will be an LCA to quantify the benefits and environmental impact of Second Life on the battery. So thank you, everybody. I finished my presentation. If you have any question, don't hesitate to ask me.
Thank you, Andy, for your presentation. We have some time to again take some questions before we go to the roundtable discussion. Maybe first question from my side. The purpose of the solderless connection is to facilitate smooth dismantling of the battery system for the second life, right? So would like to ask that in your point of view, what are the usual challenges that we are facing when we are trying to repurpose the first life batteries?
In terms of solderless connection,
In terms of
yes,
joints, welding, and other things.
Yeah, it is what we look at. It's really the voltage drop or the resistivity we have. Because if we have a bad connection, it just increase the temperature around the tabs, and in terms of security, it could be dangerous. Or so we have to have a good connection on the solderless connection and be sure that it will not increase when we have temperature rise or something else.
Okay. So in case of the proposed solutions that you have developed for two different types of battery chemistries, if this is used for during the design of the battery system, so while dismantling, the tools can be reused as well for the second life.
Yeah.
Is it true? Can you confirm this?
Yes.
Okay. Good. In terms of additional effort and cost, what would be your what is your opinion that can the current OEMs consider such type of solutions in their system design?
Sorry, can you repeat? I didn't get it.
So in terms of additional efforts and cost,
Yes.
and also efficiency, for example, what's your opinion that the current OEMs can already use these solutions in their system?
For example, for the solution we used, the connection is kind of expensive. The Molex solution is quite expensive. So we have to balance between the price and what a partner can do and produce. But it's really depend. For example, for the HV connection, it shouldn't be expensive because there is just part in glass fiber. But yeah, that's not so easy to implement it at the industrial level because it costs more than just a solder solution. But I think the LCA should be really interesting because maybe at final it's slower to have to change just one cells and not all the back, and maybe it can change and make the difference. But yeah, it's a cost at the production. Yes.
Yeah, that's a good point. That I think the economical analysis in the end of the project would give you an overview that what is beneficial, what is not. We have a question for you as well. That what kind of improvements could be made to the sandwich design for the HP pack, such as materials, additional screws. Can you explain a bit?
Okay. So in our solution, we used a material that can be improved. In fact, for our testing, we used a resin we printed at the CA. But in fact, if we have a more rigid material, we just can compress the bus bar to the tabs more powerfully. And so the connection can be improved also with a different material, and we're gonna use another material for the module level. Yes. And
Okay.
maybe, yes, additional screw, as you say, the serrat, can improve also the pressure we apply on the bus bar.
Okay. Thank you. With this, maybe we will close your individual presentation session. And thank you for your presentation. Please stay online, and I will also invite now George and Yusu for our roundtable discussion on the topic of current challenges in deploying advanced system design more and SOX software, more focus on interoperable BMS for Second Life. Good. So we had two different, specifically, let's say 3 different topics on BMS, algorithms, and mechanical solderless design. Maybe first question in general to ask you all that currently we have millions of batteries on road and vehicle, and soon, if the solution is good, they should go into the second life period. And in the second life, not only means the dismantling and the mechanical terms, but also reusing the algorithms and also the electronics components. So I would like to ask you that in your point of view, what do you see as the main or core challenge of having a feasible second life operation? Is it more feasible to do second life or better to go for recycling? And if it is second life, then what are the main challenges in your point of view? Maybe we start with George.
Oh, yes, I think that's very interesting question. In fact, we have made some reusability studies, and it shows that most of the parts for the first life of the batteries can be also used for the second life batteries. And we have also have a public deliverable about the disassembly of the batteries, that it can be done with safe use, and it seems very promising to go for second life batteries than reuse, than recycle the batteries or dismantling. And also in this phase of the project, we're also doing some economic analytics. We will have in few months some more concrete numbers to show regarding the economic aspect. So we are very promising that we will have good results on this.
Yusu, in your point of view?
Yes, from my point of view, I think that there are much more options for building second life batteries, especially knowing for that there are, for instance, only in the automotive sector, there are a lot of OEMs that have a lot of batteries in stock that they were even not used, and they can be considered as first life. And there is a very big stock of these batteries that can be used for second use. Of course, here for the case of the batteries that have already been used in some application in first life batteries, it's very critical the identification of any kind of fire or let's say to correctly diagnose the battery state of the battery at the end of this first life. Of course, there should be some batteries that it will not be cost benefit to implement them in second life batteries. For those cases, I think that recycling would be a very good option. But from our experience, there is a lot of room for developing second life batteries. And after that second life batteries, then of course go for this recycling and improvement of the life cycle of all the materials.
Okay. Yeah, it's second life is already feasible, of course. Already batteries on the market, and I have also heard third life as well. Depends on what type of application, what type of SOH, and reliability of the battery systems. But this is a reality. We will also take maybe the opinion of you, Andy.
Yes, in terms of connection between the cells is quite different if we go for repairability or if we go for a second life. Because, for example, if we just go for recyclability, we just have to get the tabs of the push cells. But if we go for Second Life, you have to make the connection with design or something else. And in terms of effort we put in, it's quite different. But yes, I think it's also I will go for the Second Life also, because they have benefits on it, and we push what the more of the battery we can, like.
Okay. Okay, then maybe let's talk about some of the challenges. We cannot address everything. So maybe related with the BMS, the call specifically asked for an interoperable BMS. In your project, George, you have proposed a hybrid BMS where some of the calculation will be in edge and some would be in the cloud. How do you ensure that there is a reliable data exchange between the edge and the cloud? And this is the first question. And during the data exchange and overall operation of the hybridization, how did you address the cyber security aspect in your project?
Okay, that's very interesting question, because if we don't have reliable exchange of data, we don't have also reliable estimations. To answer the first question regarding the cybersecurity, we ensure secure and reliable communication between the HBMS and the cloud platform by using HTTPS with SSL encryptions, which protect the data during transmission between the HBMS and the cloud platform. And in addition, we have, in order to access the cloud services, is controlled through authentication mechanism from the APIs. There is specific role for each user of the platform, and can interact only based on the access granted to them by the platform. There is different roles in the platform. I think the role that has the rights to grant access is a specific role. So it is been from the beginning of the record of the battery. So the owner of the record can give access to specific roles, and each role has specific rights. All these mechanisms provide secure and reliable communications. We have also some backup records, so in case that something happen and we lose some data, this can also be restored, the previous data. And additionally, we have, it's a little bit more technical. I'm not very related to this part because it's software development role. It is when they send the data, they have some backup server that take this data and then forward to the main server in case that the main server is overloaded. So there is many backup, let's say, roles that they give us the confidential of we will not lose any data. I don't know if I answered all your questions, Zed.
No, it's good, fine enough. Maybe the same question to hear from you, Yusu.
Sorry, there's also some deliverables public in our website. So if anyone is interested for more details, he can visit our website and see how we build it.
Okay, good. So we could not hear maybe more details on your 4-layer BMS, Yusu, from the Big Leap project. Could you explain and address the same question?
Yes, well, for the topic of the cybersecurity, it was one of the aspects that it was also addressed during the development. Even I am not an expert on this topic, but if anyone has any question on the specific measures that were taken, you can, of course, write me and I will forward the question. But of course, the cybersecurity for the cloud applications is one of the most interesting topics when dealing with cloud systems, especially if this needs to be transferred to the industry. It's one of the main concerns that many enterprises have when they are studying the possibility of implementing this this kind of systems. And of course, something that it should be addressed. In our case, we saw that the cloud layer, it was also a very important aspect of this extended BMS solution. Apart from the edge device that also has like a extended computational capability for comparing with the traditional, for instance, BMS master systems, but also these cloud applications permit, let's say, a centralized node where you can have like you can centralize the information of different batteries, because normally if you have just one BMS in one with one system, you can only gather and process the information of that single battery, but have a cloud system, at least from the point of view of these diagnosis and prognosis algorithms, allows to gather together information of different systems and improving the knowledge of your battery.
Okay, thank you. Maybe then a question for you, Andy. You presented a solution for the two different types of batteries. So what would be the connection type between modules? Because your solution is more on the cell level. Let's say for the prismatic cell, what would be the interconnection of the different modules?
Maybe I can share I will share it because it's clearer to see it. Okay, can you see my screen?
Yeah.
Okay, so here in the module, we have the pin, we've designed this kind of pin that will go into the PCB. But the link between the module will be made by this pin, the higher pin, because the pin will go through the socket and go out of the casing, and the connection will be made by another socket on the outer of the casing to join the other module. So this is the connection, the interconnection of the module.
Okay, thank you. Then maybe there is quite a lot of interest on the RUL and SOH algorithms. We can address those topics. The first topic is an usual challenge that in your first life, you do not have the whole history of the batteries, and then you need to develop or adapt algorithms in the second life. In your case, in Big Leap, Yusu, did you have the access to the first life batteries? If yes, then what type of data? If no, then how did you address the missing data?
Okay, so well, we have different use cases in Big Leap, and in each of them, different batteries from First Life are going to be used for these demonstrations of the project. So it was quite challenging because in each of the cases we have a different amount of data available from this First Life system, but again, I try to highlight like the which is the strength of this let's say transfer learning environment that we have proposed, and it's that even if we have more or less data, we are able to, of course, as much as more data is available, the efficiency of the predictions for the second life will be better. But let's say the model that we developed is able to be adapted easily with even very few data, or even with data that solely comes from the data sheet, for instance, of that battery. we are able also to adapt this model, because we have like the base knowledge of a model that was trained for another battery, for another system. But as we have there most of the knowledge for the degradation with just very few data, or even without data, but with data coming from the datasheet, or even just transferring and assuming that at the beginning we will have the same dynamics as the base model, but then once that we start operation in the second life, we start gathering this information from the second life, and we are able to adapt this model. So even in each of the cases, with or without data, we would be able to adapt our algorithm and perform the predictions for this prognosis in second life.
Okay, and what was in your case in battery to life, George or Mikhail, whoever wants to answer?
I can make a try. I don't know if Mikhail is still on the chat case. I think we use first life data just to train our model, but in both pillars we use different state of X estimators. For pillar 1 we use AES, electrochemical impedance spectroscopy, state of batteries, and in the pillar 2, because it was not the main point to track the state of X of the batteries, it was more basic models. So we use first life data just to compare the modeling. So we have a very good results, and this is the reason that we can use it. Will be more have to standardize methods, so it can be used for all kind of state of X estimators. So the main point was to compare it with our cases, but this can work for other cases.
Okay, thank you. We are running out of a bit of time, so we cannot probably answer all the questions, concerns today. So please reach out to the individuals on their email. The presentations will be shared, so you'll get their emails. Feel free to ask them the questions that you have. To finish off this roundtable, the projects are still ongoing. Some are going to finish and some still have some time. Could you quickly, briefly say that what is your next step on the topic that you have presented today? What is your next work that you will do on the topic? Maybe starting with Andy.
Yeah. Okay. So the next step will be to assemble all the module. We're gonna have the prototype of each module with the solder's collection and also the RF communication inside. So this is a big next step.
Okay, Yosu.
Yes, so in our case, we have now, let's say, finished all these developments of all the algorithms, and we are also finishing like the hardware and the software layers of the BMS. So in parallel, other partners are starting to ensemble and put all together all these batteries for the second life that will be the ones that will be used in the demonstrator. So of course, for us and for the topics that were addressed today, the next step will be to validate their implementation already with these systems of second life.
Okay, and lastly with you, George, in battery to life.
Yes, we are almost in the same phase also with almost said at this stage of the project battery life. He has moved from the development phase into the validation phase. So we're at the end of the validation phase. We had some issues of the development of the one BMS, but the technology and the methodologies developed within the project are tested, and we are ready for the real demonstration environments in the next months.
Okay, thank you. I wish you good luck onto your next steps. Once again, thank you for your nice presentations and the discussion that we have. with this, I close the roundtable discussion. And this is quite the end of the today's webinar, where we had 3 very nice presentations from different topics and from different projects. We also had a bit of Q&A and a roundtable discussion. Thanks to the audience that for joining this webinar. We will organize more webinars like this on different topics from the cluster that we have. I invite you to follow these 3 projects in LinkedIn, and also you can get the public deliverables in our websites and follow our next webinars as well. Thank you. Then have a nice rest of the day and weekend ahead. I wish you good luck. Bye.
Thank you. Bye.
Thank you very much to all.
Thank you.